ecosystem has a unique soundscape that is composed of organisms, geophysical elements, and other biotic and abiotic sources within a particular environment. Animal vocalizations, running water, construction, and rainfall are just some of the individual noise-emitting elements that could make up an environment soundscape. Thousands of species across the globe rely on sound to navigate, hunt, and communicate. To understand how animals are able to utilize sound, it's important to first understand the limited range of acoustics propagation. Sound is made up of and travels in waves. These waves come in different shapes and sizes depending on what the initial disturbance was. A wave's amplitude determines how loud the sound will be. The taller the wave, the louder the sound will be. The distance between wave peaks, or the wavelength, will determine the frequency of a wave, or how high or low the pitch of the sound is. Certain frequency ranges have specific properties that make them useful for specific tasks. For example, higher frequency sounds tend to bounce off of surfaces, whereas lower frequencies pass through many objects and thus travel much longer distances. Neither property is inherently better than the other, but each is used under different circumstances. For example, many animals, such as bats, use echolocation to navigate dark spaces and hunt their prey. They emit high frequencies that can bounce off of their prey or surroundings and back to their ears. If the sound they emitted is too low, the wave may not reflect back to them, and they will miss vital information about the environment around them. Alternatively, elephant herds often split into smaller groups as they travel to find resources. To communicate with other groups across long distances, they produce very low-frequency sounds called infrasound that can be perceived by other elephants over 10 kilometers away. Specific soundscape conditions can make this reliance on sound an effective survival tactic for many animals, but these species could be left vulnerable if sound conditions in their environment change. Currently, human activity contributes greatly to ocean soundscapes. The use for navigation and communication is an important tactic for many marine species because sound propagates much further through water than through air. When the ambient noise level in an environment is elevated, organisms must compete with these loud sounds to survive, making it more difficult for aquatic organisms like whales to communicate, navigate, and hear critical sounds from predators and prey. Not only does it interfere with their ability to hear, but in many cases, foreign noise is actually impacting their behavior. A recent study found that when narwhals are exposed to seismic air guns, which are used for surveying in the oil and gas industry, they immediately begin diving to escape from the noise. These high-intensity dives use much more energy than normal, and put the marine mammal's health at risk. Though many of the increasing instances of whale and dolphin strandings, decompression sickness, and behavioral changes have been attributed to climate change at large, more and more studies are revealing that marine sound plays a major role in the environmental pressures that these populations are already facing. Many of these discoveries linking ecosystem and organism variability to soundscapes can be attributed to a growing initiative for monitoring and evaluating environmental acoustics, of which researchers are finding more and more uses for in monitoring environmental changes, ecosystem biodiversity, and population growth. Microphones or hydrophones are equipment used for recording and monitoring sound. Recording frequency, loudness, and time are the primary functions of many sound level meters. This data can be displayed in different formats to gather specific information about the recorded sound. This spectrogram plot displays all three variables in one plot. Time is along the x-axis, the frequency is on the y-axis, and the sound pressure level, or loudness, is denoted by the color. Looking at specific patterns in this data can help identify specific behaviors, activities, and variability, such as feeding crustaceans or Canadian geese migration. Cross-referencing acoustic data with other environmental data, like wind speed or rainfall measurements, can confirm how environmental variability impacts the sound profile of an environment. From this data, curves can be generated that predict what the ambient sound level across the frequency spectrum should look like at any particular time. Then, any variations from this curve can alert researchers that something within the soundscape has changed. This figure shows a developed curve for the ambient sound level of most underwater environments with specific environmental stipulations, called the Wenz curve. This curve is graphed with frequency along the x-axis and sound pressure level on the y-axis. The curve suggests that low frequencies are primarily dictated by seismic activity and shipping levels, while the mid and upper frequency ambient noise levels are controlled by wind speeds and overall sea state conditions, like wave choppiness and temperature. This curve indicates just how much impact human activity, like shipping level, plays on the modern ocean soundscape. Knowing this, we can compare the frequencies impacted by shipping level with frequencies often used by organisms, such as the humpback whale song. This particular whale communicates primarily using frequencies under 1000 Hz, which the Henz model predicts would be most impacted by shipping levels. This kind of research helps conservation efforts know what frequencies are most likely to be impacted by environmental variation, as well as what frequencies will have the most dire environmental consequences if they were to suddenly change. One effective method for using microphones and hydrophones is in array formation. An array is a series of microphones or hydrophones that are set up in a grid or beam formation. This setup not only records sound in an area, but can provide a researcher with information about the direction of a sound. Say there are 2 microphones in a particular array. Not too far away, a bird begins to sing. Because it takes time for sound to travel, this microphone will record the bird song fractions of a second before this microphone. That minuscule difference in time lets someone looking at the acoustic data know that the bird was in this direction and area when it started to sing. More microphones or hydrophones in an array can lead to a more precise estimation about the direction of sounds. Sound travels differently through different materials because the speed of sound is a function of density, as we already explored a little bit through sound traveling underwater. By rearranging this function, the density of a medium can be determined by the speed of sound through that medium. So, by looking at array data and determining how long it took a particular sound to travel from one microphone to another, the density of the air or water could be determined. This is important because humid air, dry air, and smoggy air all have different densities, which means that determining some levels of air or water pollution and contamination could be done through acoustic monitoring. Often, environmental sound is overlooked when determining the health of an ecosystem. Acoustic monitoring of an environment soundscape can provide much more information about an environment than just what a particular organism sounds like. Sound is interrelated and connected to environmental conditions like wind, rain, seismic activity, and air quality, as well as organism activities, migration, and population dynamics. Being able to monitor so many variables through one measurement may be useful for the future of environmental conservation efforts, because using one kind of monitoring equipment could prove to be more economical, more time and resource efficient, and less environmentally invasive than performing many different kinds of environmental measurements.